All right, now there's a few more important things that I want to note. All right, and it really has to do with this posterior probability. All right, and it's really an obvious point. All right, but as the evidence gets stronger, then your posterior probability will increase. It'll get higher than a 9% chance that you actually have yellow fever in this case. If your evidence gets weaker, then that will obviously decrease your posterior probability, or the probability that you have yellow fever given the evidence of a positive test. All right, let me show you what I mean. All right, so look at these numbers right here. All right, this has to do with our false positivity rate, and what I could do is I can reduce these a lot. All right, notice the change now. Of the 10,000 people that have yellow fever, only 10 of them get a false positive. So now, if I go and recalculate my posterior probability that I actually do have yellow fever, given that the test comes back positive, well, it's come back positive 100 times so far, and 90 of those 100 times, it has been accurate. It's been a true positive. It's only been a false positive 10 out of those 100 times. And so if I recalculate it, it's not going to be 90 over 1090, it's going to be 90 over 100. All right? Of all the times that it's come back positive, it was accurate 90% of the time. And so now if I give you the test comes back positive, then I know that there's a 90% chance that you really do have it. Now why is that though? So because I made the test even better than it was before. Before it was pretty good, but now the chance of it giving a false positive is almost zero at this point. And so that's why your posterior probability increased from 9% to 90% chance. All right. Now let's do the opposite. All right. So again, this was our original data with a false positive of 10%. All right. It gives you a false positive 1,000 out of 10,000 times, or 10% of the time. Now I can make that false positivity rate even worse. All right, watch this. All right, we still have 10,000 people that don't have yellow fever, but now it gives a false positive for those people half of the time. So I've just made the test a lot worse. It gives a false positive a lot more than it was before. And so now if I recalculate this posterior probability, because this test is worse, that means my evidence is going to be worse. So if the test comes back positive, how likely are you to have yellow fever? Well, now it's going to be 90, not out of 1,090, but out of 5,090. There's 5,090 positive tests, and only 90 of them are accurate. All right, so now if the test comes back positive, there's only a 2% chance that it's accurate and that you actually have yellow fever at this point. And that's because I made the evidence worse. I made the test worse. All right, so a simple point, all right, talking about these posteriors: as the evidence gets better, then the probability that your hypothesis is true gets higher. As the evidence or your test gets worse, then the hypothesis, the chance of it being correct, get lower. All right, now there's also another really important point here. So again, this is our original table, and what we saw was that this again, all right, really good test even right here, all right. It gives a false negative only 10% of the time, all right. 10 out of 100 will give a false negative, and only 10% of the time, or 1,000 out of 10,000 times, will it give a false positive. So it's a really good test, and yet even if it comes back positive, there's only a 9% chance that that's true. Now that illustrates the important point, that if something is incredibly rare, then evidence supporting it, all right, will often be made up of false positives. That's what we're seeing right here. All right, we have all of these, we have 1,090 positive tests, but because people who have yellow fever are so rare, that what that means is that most of these positives are going to be these false positives, all right, positives for people who don't have it. And that's simply because the amount of people who have yellow fever is just really low. It's really rare. So you get a lot of, proportionately, a lot of false positives. Now I'm going to keep the sensitivity and the specificity the same, but I'm going to change how rare yellow fever is. All right. So the only thing I've changed is this column right here. And so what we see now, really the only thing I've changed is now there's 10,000 of these 20,000 people that actually have yellow fever instead of just 100. Now it's 10,000. All right. And so I kept the sensitivity rate the same. So it's still 90% of the time, if you have yellow fever, it will tell you that you have yellow fever. The only thing I've changed is how frequent or how common having yellow fever is. And it's gone from 1% to 50% at this point. All right. It's gone to being half of these 20,000 people. And so now if I recalculate this posterior probability, what's it going to be? How many people tested positive? 10,000. How many of those positives were accurate? 9,000 of those 10,000. So now, if you test positive, there's a 90% chance that you actually have yellow fever. Again, the test isn't any worse or better than it was before. The test is exactly as good as it was before. The only thing I've changed is how common it is to have yellow fever. Right, and so this commonality is actually what? It's this prior probability. Right? The prior probability is telling us how rare the thing is to start with. And if something is incredibly rare, if its prior probability to start with is incredibly low, then you need more evidence then you need really strong evidence to support the case that it's true. All right. So what I told a few minutes ago is if you make a really good test, then when it comes back positive, then you have a good warrant to believe that the person has yellow fever. All right, but if the prior probability is really low, like it is right here, then even that good test doesn't. It can only help so much. All right, because the prior probability was so low to begin with.